Alright guys, in this section we're going to be discussing techniques for verifying trigonometric identities, and the key to verifying identities is going to be our ability to use the fundamental identities that we've discussed in the previous section and the rules of algebra to rewrite trigonometric expressions. So here we have some guidelines for verifying trigonometric identities, and the first one here is to work with one side of the equation at a time. So remember, these identities are equations, and since we're going to verify them, we can't assume that both sides are equal to each other. So we're going to try to prove that or verify that they are in fact equal to each other, or that the one side is equal to the other side, and vice versa. And the way we're going to do that is to pick a side, either left or right. And as a rule of thumb, it's always better to start with the one that looks more complicated. But it doesn't mean you can't do the other side. It's just better most of the time to just start with the more complicated side first. Number two says to look for opportunities to factor an expression. And this includes also adding fractions, squaring a binomial, creating a monomial denominator, all those things that we kind of went over and did a little bit of practice on the previous section. You want to apply here. Anything that is going to factor, anything that would simplify, we're going to use anything that will help our case. Okay, number three, it says look for opportunities to use the fundamental identities. So basically, we have to just know our fundamental identities from the first section and just kind of see what fits. If anything applies, to see if that's going to help us verify uh, our given identity. Now, next, it says to when the preceding guidelines, so 1, 2, 3, don't really work, try converting all the terms to sine and cosine. And then last but not least, this guidelines finish with always try something, right? Because even if it's not the right thing, or if it's not going to really take you to the answer or any closer to verifying the identity, to the very least, it'll give you some insight to something else that you could do. Okay, here's an example of an identity that we want to verify. And we're going to go through the guidelines here to see how this works. So first, we want to pick a side here. And remember, the rule of thumb was to choose the side that looks more complicated. And clearly for us in this example is the left. So we're going to start on the left. We're not going to do anything on the right side. Notice how the numerator here is our Pythagorean identity. So that's equal to 1. And then I write the denominator again. Okay, remember I'm working on the left. I'm not going to do anything on the right side. I'm going to try to get to the right side here. Now I have a 1 on top, so that's already looking good. Now in the denominator, notice how I can use my identity, reciprocal identity, to change secant into 1 over cosine. This is square, we have the square in there. You notice how I have a cosine square, cancels out with the cosine square there, and that gives me a nice 1 in the denominator. So I have 1 over 1, and that's equal to 1, and we're done. Right? Because we arrived to the other side without doing anything to the right side. So that is verified right there. Here we have another example, and in this case, the right side is the one that looks more complicated because that's more stuff in it. We have a sum of two fractional expressions. So we're going to go ahead and start with that side, and we're going to combine the two fractions here. Notice how on the left I have just a monomial expression. So I'm going to have to somehow condense this stuff on the right to make it equal to 2 cosecant squared of beta. So I just combine the two fractions like we already know how to do. And we get that denominator is the product of the two denominators there. And we get that on top. Notice how the cosine betas cancel out on the numerator. And I have 1 plus 1 there. It's just 2 on the top. On the bottom there, denominator, I'm just going to distribute and get that difference of squares there, 1 minus cosine square of beta. We've done this several times. And notice how that's precisely my Pythagorean identity. So I change that to sine squared beta, and I'm almost there, right? I can use my reciprocal identity. 1 over sine is cosecant, and since it's square, I end up with 2 cosecant squared beta, which is exactly what I have on the left side. And it's verified. Here's another example, and in this case we have a product on the left, and we have a negative sine squared on the right. Again, the left side looks like the most complicated side, so we're going to start there. Recall your Pythagorean identity here, secant squared minus 1 and sine squared minus 1. We can replace those expressions with tangent square of x for the first factor times negative cosine square of x. And again, those are coming straight from the Pythagorean identities. Now I use my quotient identity. This says tangent is equal to sine over cosine, and since it's square, I have sine square of x divided by cosine square of x, right? And I have times negative cosine square of x. Notice how those cosine squares are going to cancel out. And I end up with my negative sine square of x, which is exactly what I have on the right side. And then there it is, it's verified. All right, so here's another example. It looks like we're also going to start on the left here. Notice how we can apply our fundamental identities, change cotangent to cosine over sine using our quotient identity, and change secant to 1 over cosine using our reciprocal identity. And right away, you see how, since we're multiplying here, the cosines actually cancel out. And you end up with 1 over sine of x, which by reciprocal identity is equal to cosecant of x, and because that's what we have on the right side. Another example here, we have cosecant x minus sine x equals to cosine times cotangent of x. Here they don't really, one side doesn't look more complicated than the other one necessarily, but I'm going to start on the left here. Since there's two terms, I change cosecant to 1 over sine, and I'm going to put it together. See what happens. Because remember, on the right side I have one term, so I'm trying to have just one term instead of two. So by combining these two terms, I get 1 minus sine squared on top, and that is your famous Pythagorean identity. Change it to cosine squared, and I have sine x on the bottom denominator. I'm going to rewrite cosine squared as cosine x times cosine x, and all of that is divided by sine x. Always keep in mind where you're trying to go to. So I'm going to see how take one of the cosines and divide it by the sine. Using my quotient identity, I know that is equal to cotangent. And so I have cosine of x times cotangent of x, and that's exactly what I have on the right side. And then we're done there. It's verified. Now, just to show you how, in the same example here, just to show you that you could do or verify the same identity but work in the other side. Just to kind of show you that it works either way, I'm going to start on the right side here. And if you've already done one side, you already have enough insight to do it. Sometimes it's easier to you see it one way or see it the other. Again, the rule of thumb is to kind of start on the more complicated side, but you can verify it starting at any other side. You got to pick one side though. All right, so notice how I'm kind of going backwards of what I did on the first one, on the first time that I did it when I started on the left. So if you notice how to be able to prove it or show or verify the same identity going on the other side, I'm working backwards of what I did on the previous one there on the other side. But it works the same way, and we get to the same conclusion. As long as you go from one side to the other, we accomplish the same thing. There it's verified. So same problem, just different, and starting at different sides. Okay, so here we have another example, and on this one, I could work either side, but I'm going to start on the right here because we've seen a technique using the conjugate idea to rewrite this expression on the right so that we don't have a fractional form. And notice how we don't have a fraction on the left, so I'm going to use this technique here to rewrite this so that it's not in a fractional form. And I do it by multiplying top and bottom, numerator and denominator, by 1 plus cosine of x. Notice how on the top I end up with sine x times 1 plus cosine of x, and I'm not going to distribute that right now. I'll leave it in a factor form. And on the bottom denominator, I am distributing 1 minus cosine times 1 plus cosine, and that gives me the difference of squares that we're so familiar with, 1 minus cosine squared, and that's again our Pythagorean identity. And that's the whole purpose of this trick, that by multiplying top and bottom by that, I can use the Pythagorean identity on the denominator and convert that to a monomial expression. You notice how that sign cancels out. I have a sine x on top, sine squared on the bottom, so one of them cancels out, and I end up with 1 plus cosine x on the top divided by sine of x. I can split the sine into both terms here, and I can do that because I have just one expression, one monomial expression on the bottom denominator. And so splitting it into the two terms here, I get the cosecant x plus cotangent x using our fundamental identities. Here in this example, we have two fractions here. So you can take your pick here. One side is not necessarily harder or more difficult than the other one, but we're going to start on the left here this time. Notice how I can use my Pythagorean identity to change tangent square of theta to secant square theta minus 1. And guys, remember, this is not the only way of doing or tackling these problems, but it is one way. And we're going to try to come up with the more efficient ways that don't take us too long to verify. And if you remember your factoring, the numerator has a difference of squares. I can split it into those two factors. And I do that so that I can simplify the denominator there. That's how those two cancel out. And I end up with just secant of theta minus 1. You may ask, I don't have a fraction, and I have a fraction on the other side. So I'm going to have to keep going here and change the secant to 1 over cosine minus 1, and then try to combine those two terms to see what we get. We combine 1 over cosine minus 1, I end up with 1 minus cosine on top, all of that divided by cosine of theta. And that is exactly what I have on the right side. So then we're done. It's verified. Okay, so we'll do another example here. We have tangent cubed of x is equal to tangent x times secant square minus tangent of x. I'm going to start on the right side this time since it has more stuff, more terms, and I start by factoring tangent x. I automatically identify that both terms have tangent in common. I factored it out. Notice how right away, as soon as I do that, secant square of x minus 1 is exactly my Pythagorean identity, right? So I can change that to tangent square of x, and I think you can see what to do from there. Let's combine the two, and I end up with my tangent cubed of x, which is what we have on the left side, and we're done. Okay, so one last example here. We have sine cube of x times cosine to the fourth of x equal to cosine to the fourth minus cosine to the sixth, all of that multiplied times sine. I'm going to start on the right here. I can go ahead and factor cosine to the fourth on that parenthesis, and I end up with cosine to the fourth times 1 minus cosine squared, all of that times sine of x. Notice how my expression in the parentheses is my Pythagorean identity. You can see how Pythagorean identity comes up almost everywhere. And change that to sine square of x. And remember, I still have sine of x there, which I can combine with the sine square and get sine cubed of x. And yeah, we can always change the order. In a product, the order of the factors doesn't change the result. So changing the order here of the product gives us what we have on the left side. And then there it is. It's verified.